Example 6, convert each polar equation to a rectangular equation. Now we're going to actually think about this logically, and we're going to also do this algebraically. Let's first think about this logically. And in order to do that, I want us to think about just the equation y equals 3. And so what I'm doing right now is I'm just sketching in some axes. And if we wanted to sketch y equals 3, a lot of you might remember that that's just a line that literally goes through y equals 3. Okay. Y equals 3 is just the collection of all the points where the y value is equal to 3. And let me write that a little bit neater. There we go. That's all the equation y equals 3 is. Okay. And so we're going to say the same thing over here. This is going to be it's going to be the collection of all points where r is equal to 3 and theta can be anything. So let's go ahead and we're going to try and sketch that. Alright, here are our axes, and I want to label up to 3 in every direction. And the next thing I'm going to do is just plot some points where r is equal to 3. Again, it doesn't actually matter what theta is here. So r equals 3 just means we're 3 units from the origin. So some easy spots would be maybe where y equals 3, x equals 0, or x equals 3, y equals 0, or maybe these other two. Right? Those are all easy. But the question is if you let r equal 3 and you let theta vary, what shape are we going to get? And what you would see is you would get a circle. But I probably haven't scaled this perfectly. So all I'm doing is I'm letting r stay fixed at 3 and letting theta vary. And what this should create here is a circle. Now, how do we verify this algebraically? Well, it's going to require us to be a little tricky. What we're going to have to do is actually square each side of this equation. And then some of you might remember, we just learned this, so you might not remember it yet, that r squared there is equal to x squared plus y squared. Right? If we move back up here, there it is. X squared plus y squared equals r squared. Right, and so we have x squared plus y squared equals 3 squared. And now we actually have an equation that just has x's and y's and it has no r's and thetas. So this is the equation. And this is a circle centered at 0, 0 with radius 3. All right, let's go try another example. Actually, before we try one more example, let me just write one thing down here, just in case you don't remember. If we want the circle with center AB and radius r, the equation is x minus a squared plus y minus b squared is equal to r squared. Okay. And so if you didn't remember that, hopefully that makes this last example a little bit easier. All right, we have theta equals 3, and this one's actually kind of tricky like the last one. Okay? And this is because now we have to let theta equal 3, but let r vary. Okay, let's sketch in our axes. And so this is one we actually can't graph on the calculator, because you might remember on the calculator when we were in polar mode, the equations are r equals, not theta equals. Okay. But if you were to think about this, this right here is about 3.14 radians. If we rotated from the positive x-axis to the negative x-axis, that's about 3.14 radians. So 3 radians would be some angle maybe off like this, pretty close to 3.14. Okay. But the question is if this here is along theta equals 3, what happens is we let the radius vary. Okay. Well, we might get, I'm going to actually try and put one in between here. Maybe we'd have a point here, right? Looks like it's off at about the same angle. And maybe I could even actually go a little bit lower with that middle one. There we go. Yeah, those all look in line, right? Now, this is if r is positive. Well, what happens if r is negative? You might remember it means we just rotate the point 180 degrees. So for a negative r, we might have a point here. And another one, we might have a point here. And if we were to connect all these, is what we'd end up with is a line. And let's see if I can move this over those points. I don't know that I'm going to be able to. Might just have to sketch it by hand. There we go. There's our line. Now the question is, how do we verify this algebraically? And since this original equation up here was so simple, it actually required us to be clever. We had to square each side of the equation. And because this one's simple here, it's going to also require that we be kind of clever. If we were to take tangent of both sides of the equation, we'd get this. But you know what tangent of theta is equal to. It's equal to y over x. And the question is well, why was that helpful to make that replacement? Well, now my equation no longer has thetas or r's. It only has y's and x's, which means that we have here a equation that is in Cartesian coordinates or rectangular coordinates. And this makes sense too, right? This is just a constant times x, which is exactly what this line looks like. A constant times x. Its y-intercept is 0. All right, let's take a look at another one. So here you can see we have this cosine theta and this sine theta. Well, you might remember we have a couple rules here. X equals r cosine theta y equals r sine theta. So you can see that if these had those r's next to them, we could replace them with x's and y's. Okay? So to get those r's there, we could do that in a couple ways. I mean, one is you could multiply the numerator and denominator by r, but I don't think we have to do anything that tricky. Let's maybe just multiply both sides of this equation by what's in the denominator. Okay. So if we do that, we're going to have r times cosine of theta minus 2 sine theta. And then over on the right, we'll have 5 times cosine of theta minus 2 sine theta. And again, we were multiplying both sides of the equation by this. And the whole purpose of that is here on the right side, we get a little bit of cancellation. So this turns into, I'm going to distribute this r through, turns into r cosine theta minus 2r sine theta. And on the right, we just have 5. And now you can see we can replace r cosine theta with an x and the r sine theta with a y, so minus 2y. And so now we have just x's and y's, so we are in Cartesian coordinates. And if we wanted to go one step further, we could just solve it for y. Let's go ahead and subtract by x on each side, and then finally divide by minus 2. And so that leaves us with y is equal to minus 5/2 plus x over 2, or 1/2 x.